out, my microphone's on. So how many of you were able to access the PowerPoint video last night? So most people. It was describing to you how to use regression to explain the relationship between two variables, an x variable and a y variable, and then use that relationship to make predictions. Okay, so what we're going to do today is an activity that you're going to get some data that has x variables and y variables, and you're going to make predictions, and you're going to test your model and see how it works. Okay, so I've handed out a activity sheet that describes what's going to happen. What I'd like you to do is get into groups of 4. There are 17 of you, which means that that's 4 groups of 4 and 1 group of 5. Okay, so I'd like to have you get into groups of 4 and 5, and then once you've decided on your group, I'd like you to take a couple of minutes to read the first few paragraphs of the activity sheet so that you can see what's going to happen today. And while you're doing that, I'm going to be passing out some materials. Okay, so gather yourselves around, and you can move the desks and things like that as much as you want. Okay. In your group, you each have at least 4 people. You're going to have 1 person holding the yardstick. You're going to have 1 person dropping the ball, 1 person looking to see how high the ball bounces back, and 1 person recording your data. If you have 5 people in your group, you're going to have 2 people looking to see how high the ball bounces back, and you'll have to resolve any disagreements as to how high the bounce was between yourselves before you record it. Okay? Is everybody sure what's going on now? Okay, let's gather some data. You're gonna bounce the ball 3 times from each height and get 3 different values. Okay. You can choose your own heights for the other ones.
Yeah, I'll write it down. Somebody's got to be catching that. Say when you're ready. 19? Yeah. 36, 3. 20? So y'all just want to go down to 30? 17? So just call it.
So what size you want to do next? We should go down. Clearly we can't go up. Yeah, exactly. Let's go 30. Let's just down. You want to do 30? Yeah, let's do 30. No. 30. 30? I know it's okay. That was like 21, yeah.
Then we'll do
30.
Okay, let's just make it
30.
15, 14, 12, 10, 5.
20,
15,
Yeah, somewhere right there.
15, 14.
Yeah, we could do it too.
Okay, so everybody's busy entering data into your calculators. While you're doing that, I want you to make sure that you have 30 pieces of information in each of your 2 lists, and that the lists are paired. So if you have a 36 next to a 21 on your piece of paper, then the 36 and the 21 need to be in the same row on your stat list. Okay? Okay, So the next thing that you want to do once your data is in the calculator is to make a scatter plot of it. And when you do the scatter plot choice in your calculator, you do second y equals, you choose one of the graphs, you select scatter plot. One of the things that you need to put it, well, two of the things that you need to put in there are X list and Y list, right? And in the X list, you're going to put in the X variables, the name of the list where you put the X variables, and in the Y list, you're going to put the name of the list where you put the Y variables. What's the difference between X and Y? How do you know which one's X and which one's Y?
X is the one that you set yourself, so it's going to be the drop height.
Well put. X is the one that you set yourself. So in this example, it's the drop height. Okay? So you want to think in terms of input and output. X is the input variable, Y is the output variable. You chose the drop height, the ball chose the rebound height, right? So the X list is the list where you put the drop heights, and the Y list is the list where you put the rebound heights. Okay? Okay, so a lot of people are getting ahead of me, so let me have you guys put up the scatter plot on your calculators right now. So that is second y equals, and choose the scatter plot and put in the X list and the Y list. And then go to zoom, and the ninth option is zoom stat, and that'll give you your scatter plot. Okay, so I want at least one person in each group to have your scatter plot up. Okay. Now at this point, we want to ask ourselves a couple of questions. Is there a relationship between the X's and the Y's in your picture?
Yes.
Yes, and how would you describe that relationship? Positive. How do we know positive versus negative? What's the difference?
It's going up.
Yeah, it's going up. As the X's increase, the Y's increase. So if you see an upward slant, that's a positive relationship, okay? So we know that there's a positive relationship. Does it look like that relationship is linear, or is there some sort of curve to it? It's roughly linear. You never get perfect, by the way, but it's roughly linear. So because we've got yes answers to both of those questions, there's a relationship and that relationship looks linear, that makes it allowed for us to use regression. If we chose any other answer to those questions, then we would not be able to do linear regression. Okay? Okay, so now that we know that there's a relationship, we want to quantify the relationship, okay? And that's what you're doing when you go to the lin-reg option. So if you go to Stat and arrow over to Calc and choose, I think it's the 8th option, lin-reg, when it comes up, then you have to enter in the X's, comma, the Y's, right? And so you have to answer the same question that you did with the scatter plot, which is which one's X and which one's Y. And we already answered that. Which one was X? The drop heights. And which one was Y? The rebound heights. So you're going to enter in, if the drop heights were in L1, you'll do second 1 for L1, and then comma, second 2 if you entered the rebound heights in L2. And you should have 4 numbers on your screen. If you only have 2 numbers, are there some people who only have 2 numbers? Okay, if you only have 2 numbers, you need to turn the diagnostics on. And I need to look at somebody's calculator to tell you how to do that. Okay, so you go to second 0 to get your catalog, and then you arrow down until it says diagnostic on. Just keep going until you get to the D's and hit diagnostic. No, you should have 4 numbers on your screen. An A, a B, an R squared, and an R. Okay. If you didn't, then you don't have your diagnostics on. Okay? Okay, so when you hit diagnostic on, select it and then hit enter, and it should say done on your screen. Okay. Once that happens, then go back to the lin-reg, stat, calc, lin-reg, it was the 8th choice, then L1, comma, L2, and hit enter. Okay, so you should have 4 numbers, A, B, R squared, and R. And by the way, people in the same group should have exactly the same 4 numbers, right? So double check, compare, make sure that you have exactly the same 4 numbers if you're in the same group. So I'm getting the question about how many decimal places to go to. And in different sciences, you'll have a different answer to that question. So physicists will want more decimal places than, I don't know, biologists, okay? So because I don't know which science you're going to be applying this to, I'm going to give you a rule of thumb that is you go 1 more decimal place than what your data was. Okay, so if you were recording to data to within a 1/2 inch, that's 1 decimal place, so you'll want 2 decimal places of accuracy. Does that make sense? So 1 more decimal place than your data had, okay? And that rule, by the way, changes if you're in a situation where they have a rule for that, okay? So now you have 4 numbers, A, B, R, and R squared. Let's talk about R. Does anybody remember what R was? Correlation, right? R is the correlation. And R can be a number that is either positive or negative, and it's between -1 and +1. What R did you get? All 4 groups. What R did you get, this group? 0.99. What did your group get? 0.98. What did you get? 0.99. What did you get?
0.97.
0.97. That is about as close to 1 as you're ever going to get with real data. So what does that mean that your R is really, really close to 1?
So we did a good job. And our data is correct, and our measurements are good.
It's not that your measurements are correct, because you could measure things and there could be a lot of randomness. What it's saying is that the drop height has a really strong effect on the rebound height, that there is a very strong positive correlation between these 2 values, okay? Now I just used the catchphrase cause and effect, and that means that I have to do the jumping up and down of any statistician. Are you ready? Ready?
Yeah.
Correlation is not causation, right? Just because 2 things are correlated doesn't mean that one causes the other, right? 2 things can be correlated for 4 reasons. A causes B, B causes A, they're both caused by something else. Coincidence, okay? So in this case, we're pretty sure that there's a causation, but that's because we have other information about where the data came from. But just looking at a strong correlation doesn't mean that A caused B, okay? We've got the correlation. What was R squared?
0.947.
0.947, maybe 0.95, roughly. What does that mean, R squared? Does anybody remember the vocabulary word for R squared? No, R is the correlation coefficient. R squared is the coefficient of determination. So that's complicated. And that's saying this is the percent of the variation in Y that is explained by variation in X. So in other words, there's some variation in Y just anyway. So for example, when you dropped the ball from 36 inches, you didn't get the same answer all 3 times, right? Why didn't you get the same answer all 3 times?
Error.
Error. Okay, first of all, this measurement tool, not all that accurate, right? Secondly, how do I know I'm holding it at exactly 36 inches instead of 36.2 or 35.9, right? So there are errors that come in the measurement, but the thing is, the X didn't change. The X stayed the same and there was some change in the Y, right? Now, When you dropped it at 36 inches and when you dropped it at 12 inches, you got different y values. And so some of those difference in the y values was explained by the fact that it's a yardstick, and I don't know exactly where I'm dropping it, but some of it is explained by the fact that I'm dropping it from different heights. And so then the question is, which percent is from which reason? And that's what R squared measures. R squared measures what percent of the variation is due to the change in the x. And in this case, you got something close to 95%, which is huge. That's basically saying all the variation in y, except for this little tiny bit. Does that make sense? Okay, so that's called the coefficient of determination. That's what R squared is. Okay, so then we've got A and B. And one of them's the slope and one of them's the intercept. And I don't know about you, but I never remember which one. Okay? And that's also because, by the way, there are 2 lin regs in your calculator, and if you chose option 4 instead of option 8, they switch order. So because of that, you're going to want to look at the top of the output, and it says y equals a plus bx. It does say that, right?
Yeah.
Okay. Because I always forget. It could have been ax plus b. So it says y equals a plus bx. So that means that b is the thing that's multiplying x. So it's the slope of the line. So what was your b? This group here, what was your b? 0.66. This group here, what was your b? 0.65. 0.66. What was your b? 0.78. 0.78. What was your b? 0.5. Okay, so 0.78, 0.66, 0.5, those are your slopes, and they are describing how much the y value is going to change if the x value increases by 1 unit. Okay, so what does that mean? Let's say I drop the ball from 24 inches and it bounces up to 12 inches. I'm pretty sure that didn't happen, but let's pretend it did. Okay, dropped it from 24, it rebounded to 12. If I dropped it from 25, which is 1 more than 24, then I would expect it to rebound to 12 plus 0.6, 12.6, because an increase in the x variable by 1 increases the y variable by the amount of the slope. Okay? Make sense? Okay. Why did you guys get different slopes? Different balls, right? We had some racket balls and some ping pong balls. Who had the ping pong ball? You guys had the ping pong ball and all of you had racket balls, right? So that's going to make a big difference. And the other thing that's going to make a big difference is was the yardstick tilted, was the person who was spotting looking at it straight on or from below or from above. So there are a lot of ways that that could change, right? Okay, so we've done 3 of the 4. The last one is A, right? And it's y equals a plus bx. A is the intercept of the line, okay? And that is interpreted as this is the value that y would be if x was 0, okay? Now, in our case, if x is 0, what does that mean physically? You didn't drop the ball. You just sort of set it on the ground next to the yardstick, okay? So what do we expect y to be? 0. Was it 0? Mm-mm. Is it close to 0? Well, the problem, of course, is that there's randomness here. Okay, so we've got 4 numbers and we've interpreted them. I want you to answer a few more questions and I'll stop you when we get to the prediction part, okay? So go through your worksheet and answer a few more questions and I'll stop you again in a few. Okay, so why do we care, right? We just did this model and we dropped balls and we got the y equals a plus bx. Why? What's that good for? Well, what that's good for is to use that model to predict what will happen if we were to drop the ball again. Okay? So I want you to pick a number that is on your yardstick that is not one of the heights that you already dropped the ball from. Okay? Have that in your head. Okay? Now, is that number an X value or a Y value? That's an X. Why is that an X?
The one that we chose.
It's what you choose, right? It's the input. Okay, so you have an equation, y equals a plus bx, right? Put that x into that equation, y equals a plus bx. In other words, multiply it by b and add a and get what y is, okay? When you do that, you're getting a y value, and what is y for this example? The rebound height, right? X is the drop height and y is the rebound height. So in other words, you're taking a drop height that you haven't dropped the ball from, and you're predicting what the rebound height will be, okay? So go ahead and get that value, and then we're going to check your prediction by actually dropping the ball a few times from that height, okay? So go ahead and do that. Okay, so how did your prediction work? Did it work?
Right on. We were pretty close.
All right. It's nice when stuff works, isn't it?
Yeah.
Okay, so let's talk about when the stuff wouldn't work, right? Because we have to know when it's appropriate to use this model and when it's not appropriate to use this model, okay? What if I take your ball away from you and give you a ping pong ball? Would your model still work? Of course not. Different ball, right? What if, you know, I'm pretty sure that all your drop heights were between 0 and 36, right? Why am I pretty sure of that? Because I gave you a meter stick, a yardstick, so pretty sure of that. So what if I told you to drop the ball off the roof of the building? Would your model still predict the rebound height pretty well?
You have acceleration due to gravity, so it's going to throw off.
Basically, the model's going to change outside of the range of the data that you modeled, right? So, for example, acceleration due to gravity could make the model be more quadratic than linear. That means there could be some faster acceleration than what we're accounting for with the model that we're using. So that means that our model is pretty accurate for numbers between 0 and 36 and still okay for numbers around 40. But once we get really far from the set of data for which we created our model, then the model's just not that good anymore, okay? That idea of using a model to predict outside the range of where the data were, that's called extrapolation. And that's just not as accurate a process as interpolation. Interpolation is predicting within the range of the data, okay? And by the way, there are other things that would make the model not work right. So you all put the yardstick on the desk and dropped the ball onto the desk, right? Why did you do that? Because the floor is carpeted, right? So if I were to tell you, okay, now you have to drop it onto the floor, would your model still work? No, because balls don't bounce as well off of carpet as they do off of a hard surface, right? So when you're using a model to make predictions, you need to know where the data that made the model came from. Does that make sense? Okay. Now, there are a couple of other points that I want to make, and then we'll be done with this activity. First of all, we did a bunch of different things today. We collected data. We put the data into the calculation device. It's not always a calculator. Sometimes it's a computer program, right? We analyzed the data, and we made a prediction. And then we tested our prediction. Which of those steps took all the time? Collecting the data, right? And which of those steps do we spend all of our time in a classroom in a college campus talking about? Interpreting. The analysis and the interpretation of the data. But I want you to remember that when you get out into the real world, the hard part of any statistical analysis is the data collection part. And that's because if you collect your data badly, your model doesn't work. So you have to be careful to make sure that everybody who's part of your data collection knows what they're supposed to do. Now, if you have a group with only 5 people in it, it's fairly straightforward to make sure that everybody knows what they're supposed to do. But imagine a very large data collection process, like a clinical trial for drug testing. Here you're talking about thousands of people being part of the data collection effort. And you have to put into place procedures for those people to follow that are well enough written out and clearly enough stated so that they can collect your data appropriately so that your model will work. Does that make sense? Okay, so as you do the rest of this class and you learn how to analyze data, I want you to keep in the back of your head that this is actually the most straightforward part of the process in the real world, the analysis of the data. In the real world, the hard part is making sure that you collect the data accurately.